G'day and welcome back to RC Model Reviews, and this Tech Tuesday we're focusing on one of the sort of underrated components in the electronics field. It's a simple device, but it can do some fantastically amazing things. A lot of people don't realize what the humble diode can actually do. The humble diode can be many things. It can convert alternating current to direct current. It can block the flow of unwanted direct current. It can protect devices against voltage surges. It can protect against reverse polarity. It can actually act as a tuning element in a tuned circuit for transmitter or receiver. It can produce light, and it can also act as a switch. All those things and more from the humble diode. Let's take a look at it. And here is one of those humble diodes. This is a 1N4007. That's the name given to it. Its role is a rectifier. It's designed to act as a one-way valve. I'll show you on the whiteboard in a minute about this, but it's a one-way valve. It lets electricity flow in one direction, but not in another direction. And we're going to do a simple little breadboard experiment here just to show that this is actually what they do. Okay, ladies and gentlemen, here we have a super simple circuit to show you how a diode works in its rectifying mode. What I've got here couldn't be simpler. This is a voltage, it's about 3 volts going into this breadboard here. We have a diode down here connected to a light emitting diode. This could be a light bulb, it could be a motor, it could be anything that's going to use electrical power. And then this goes off to the negative voltage here. So in theory we should have a current, there should be current flowing and the little light should be on, but it's not, because the circuit I've drawn is this one. We have positive, we have a diode, and this is the symbol for a diode, which has got like a triangle pointing to a barrier. And there's our light or our motor or whatever. But there's no current flowing through this circuit, so this light doesn't light up. Why is that? Well, because we have the diode in what we call the reversed biased condition. As I say, rectifier diodes are like a one-way valve. So imagine that this is a water wheel and this is a one-way water valve, and the water's trying to push through, but when it comes this way, the valve slams shut, no water flows, nothing happens, no work is done, no energy is produced, nothing happens down here. This is with our diode in the reversed biased condition. It is an open switch, nothing can flow. No electricity can flow through the diode like that. So what happens if we make this circuit? All we're going to do is turn that diode around so that this time it's pointing towards the load. I'm going to do it while you watch, and hopefully I won't kill myself and there'll be no smoke. Right, let's plug this back into exactly the same holes or near about. Tight fit on the board, this one. And I'm going to plug it into this voltage up here, and with any luck, if it'll go in the damp, there we go, look, the light has illuminated. So what's happening now, we're looking at this circuit now. So the electricity comes along, it enters the diode, and because it's traveling in the same direction as the triangle, it will pass through that barrier and then do some work. This, as I say, could be a light, a motor, could be anything that's electrically powered. So suddenly the electricity can flow. This one-way valve lets the electricity flow through the circuit, and it's almost as if this wasn't here anymore. It's almost as if we had just shorted out that little diode. Not quite the same, but almost. So, hey, there we go. Now this could be applied in a number of ways. Imagine that, for example, we had a video transmitter here instead of a light. There we go, a little video transmitter. In this situation, video transmitter would work as normal. If we had it over here, and say we reversed it, let's just say we accidentally plugged it in backwards. So we had 2 wires coming off here, and we accidentally plugged those wires in backwards to our power source. What would happen is we'd end up with a situation where we had positive down here and negative up there. So again, the current would try and flow the wrong way through the diode. The diode would block the flow of current, so this wouldn't work. There'd be no current to damage this or blow it up. If you didn't have a diode there, then the power would come through, smoke would come out, and that'd be the end of your transmitter. But with a diode in there, which is what we call polarity protection now, that means that if you plug it in backwards, it simply doesn't work. So you might think, oh, why don't all things have diodes in series with them so that you can't damage them by plugging them in backwards? And I'm going to show you why. Because I mentioned that this is almost acts like a short circuit, almost acts like it's not there when you've got current flowing the right direction, but it's not exactly like a short circuit. It's not exactly, it doesn't totally disappear, because if I get my multimeter here and I put my multimeter across this diode like this, you watch what happens on the multimeter. There we go, we've got 0.727 of a volt across this diode. So some of the voltage is lost across the diode. It's not a perfect one-way switch. There's always a bit of loss when electricity flows through it. So we're going to lose about 0.7 of a volt on your average rectifier diode when you pass current through it. So in the case of something which may be running from a battery pack, that reduces the minimum voltage you can use across here because you're wasting 0.7 of a volt. So if you're running it on, for example, an FPV system, then as your voltage from your flight pack drops, the FPV system will cut out more quickly than if you didn't have the diode there, because let's say the FPV system drops out, and I know the old board cameras used to do this, they were terrible. They would drop out at about 9 volts. And so if you flew your flight pack down to 9 volts on a 3-cell pack, you'd lose video before the plane actually stopped flying and you lost control. Put a diode in there, you'd actually lose video a lot quicker because they'd drop out at 9.7 volts, because 0.7 of that 9.7 would be lost across the diode and you'd only get 9 volts across this bit. So that's why we don't use diodes across everything, because although it seems like it'd be really easy, it's not quite so easy. But there is a slight way around that, and I'll show you that now. Okay, if I want to use a diode to protect something in this way, then I won't use one of these 1N4007, these power rectifier diodes. I'll use one of these. It looks exactly the same, doesn't it? But it's not quite. This is what's called a Schottky or a Schottky diode, depending on which school you went to. And it works exactly the same as this, but it has a lower voltage drop across it when it's conducting current. So I'm going to take this diode out, the 1N4007, and I'm going to put in the Schottky diode, which looks, to all intents and purposes, to be exactly the same. Right, now we're going to measure the voltage across that. Everything works exactly the same, there's no difference. So let's measure the voltage across that and see what it is. I should leave my multimeter in shot for this, shouldn't I? It makes it much easier for you to see. Okay, put my meter probes across the diode, and we get, instead of 0.7 volts, 0.3 volts. So this has a much lower voltage loss across it than the rectifier diode. And you might think, whoa, that's great, so why don't they use those all the time? Well, there are other issues with Schottky diodes. They have a slightly higher, what we call leakage current, which is the amount of current that can trickle through against the block that's in there when it's reverse biased. But yeah, Schottky diodes are the perfect protection diodes because you don't waste so much voltage. You only waste half the voltage across the diode that you would with a rectifier diode like a 1N4001. It's very confusing, isn't it? But let's suffice to say, this is why diodes, there are so many diodes and you need to use the right one for the job. And I'm thinking this is probably the most common use you as a modeler would have for using a diode outside of the way they're already built into a lot of our circuitry. So reverse polarity protection is the primary way, and if you're going to do that, you need a Schottky diode. This is a 1 amp Schottky diode, but it's only rated to 50 volts. And this one that we took out, 1,000 volts, 1,000 volts. So that's another reason why we don't use Schottkys for everything, because they tend to have a lower voltage rating, and therefore you can't operate them on high voltage systems. But there we go, very basic stuff. Now I'm going to show you another form of diode. I'm going to show you how a diode can turn AC into DC. Okay, here we go. Now we're going to look at how AC becomes DC with the help of a diode. What I've got here, I'll just move my camera over, is a signal generator that's generating a sine wave. We all know what a sine wave looks like. And it's feeding that out. This is the circuit representation of my signal generator. It's feeding that AC sine wave into my diode. There. And we're going to use the oscilloscope now. I'm measuring over here. You can see that's the lovely sine wave that is being produced by the signal generator. And I'm measuring that at the moment on there. Now I'm going to move my oscilloscope probe over to there on the other side of the diode. And I think you can probably work out already what's going to happen. I'll show you this oscilloscope as I move the probe. Let's move the probe now onto the other side of the diode, and woohoo, look at that. Half of that sine wave is missing, because when the voltage tries to go below 0 volts, the diode turns off. It says, no, I'm not having any of that. So it blocks it. So instead of the voltage going down there to negative, it just goes straight across. Now there is a small, it's not exactly 0 because we've got that little 0.7 or 0.3 volts of the diode to contend with. So in this case, it goes down there and it goes along there. So there we go. That's how we can convert AC into DC. But this is pretty crap DC. It is, in fact, just pulses. So how would we make that into a nice smooth voltage? Well, remember our friend the capacitor? I think we spoke about them last time in our TechTuesday. So I'm going to let's go back to the circuit diagram. I'll show you what I'm going to do, and we'll see if it's going to work in this case. Let me just pull out a bit here. I'm going to put a capacitor into our circuit. I'm going to put it here, like this. And if you remember what we learnt last time, that should fill in those bumps. So let's try it out and see. Right, here is the capacitor I'm going to use. It is an electrolytic. You can see that. I haven't got one of the legs in, so at the moment we still have our half sine wave here on the oscilloscope. And I'm going to plug that electrolytic into the circuit and we'll see what happens. Look at that. Did you see it? The voltage came up to the peak of those things. It's actually filled in the gap. So now we've taken let me go back to the other side of this diode. Ooh. Here's our AC on the one side of the diode. Here's our DC on the other. That's how diodes can turn AC into DC. This is used a lot, of course, in power supplies. You know, your battery chargers and just about anything that plugs into your mains voltage uses one of these rectifier circuits to turn the AC from your 110 volts or your 230 volts into the DC that most things use. You know, whether it's a 5-volt USB power supply or something, it all involves turning AC into DC. That's what we've done here. The simplest of circuit diagrams, as you can see, and we have used what we learnt last week about capacitors and what we've learnt today about diodes to make that work. Isn't that simple? There you go. So there is another reason why you might use a circuit like this in the hobby, and that is if you've got a lot of noise on your signal, you know, perhaps it's coming from a battery which has got noisy ESCs. If you put a low drop diode like a Schottky diode in there and a capacitor, then you can really significantly reduce the amount of noise that goes through to your video transmitter, your camera, your RC gear, or whatever else is running off this power supply. So this little Schottky diode and capacitor becomes a really, really effective noise filter. When you think of it, that's what it's doing here when it does that rectification. If we look at this is without noise filtering, and this is with noise filtering. So there you go, you can get rid of a lot of that noise, and that's, again, Schottky diode and a capacitor makes a huge difference. And I might do some practical, I think I already did a noise filter using inductors, but you can use capacitors and diodes to get really, really effective noise filtering. I might do a little project on that later on. So that's our rectifier diodes. That's cool stuff that you can do with them. But now I'm going to look at another aspect of diodes, and that is how you can use them as a switch. How can you use a diode as a switch? Sounds crazy, doesn't it? But one of the most common uses used to be using diodes for switches. Show you how that works now. Okay, once again, we've got the breadboard set up here so you can see what's going on. I've got a signal generator here again, generating a sine wave signal. It's going into this circuit down here, and I've drawn a diagram of that circuit so you can see what's involved. Let me just pull out a bit so it fills the screen. Okay, now here is the circuit. It's pretty straightforward. I'll walk you through it. We have a signal coming in. This is our sine wave. Let me just draw a little squiggle on. Oh, I've actually drawn a squiggle. So this is our sine wave signal here, or it can be any signal. This could be a video signal. It could be an audio signal. It could be anything, any kind of signal, any alternating current signal that you want to switch. Comes in here through a capacitor because we don't want any DC voltage in here. We're going to feed DC voltage in the other side here. So it comes in here, comes to our diode, and then goes out there. There's two conditions. When the switch is off, then the signal won't pass through the diode, and I'll tell you why in a moment. But when the switch is on, the signal will pass through the diode. So how do we convince the diode to turn from being an open switch to a closed switch? Well, it's just basically a case of passing some current through it. So here we have a resistor, which provides a DC path for current, which we call a bias current. And here we have another resistor, which is basically we're just measuring the voltage across that. So the AC will come through and out there, and we'll have let's draw a little circuit diagram symbol here for ground, because this is ground. And the AC signal here also, the other side of it goes to ground. So everything's referenced to the ground here. But basically what happens is when you apply a voltage to a diode, unless it reaches the 0.7 volts required for it to start conducting, you know, we have 0.7 volts across our diode when it's passing current, until you get 0.7 volts across the diode, then it doesn't pass any current at all. So if we put a signal in here and the size of that signal isn't big enough to reach 0.7 volts, then it won't pass through the diode, because until you have current flowing, the diode is an open switch. So normally, without any voltage on here, if this is a smaller signal, say it's only up to 0.6 volts in terms of its size, then it won't pass through the diode and come out here. Let me just label in and out here because it's important. In and out. So if the voltage of the signal doesn't reach a high enough level to turn that diode on to start passing through the diode, nothing will come through. And I'm going to show you on the oscilloscope here. I'll show you on my little breadboard so you can see. Now, I've got my oscilloscope probe on here. I've got my diodes and everything there. And at the moment, I have my bench power supply coming here, and that is biasing the diode on. So what's happening is we've got a voltage up here. That voltage is flowing through the resistor, through the diode, through that resistor, and out. So there is the 0.7 volts required to make the diode conduct to become a forward pass to switch on is provided by the current flowing through this resistor. That means the diode then becomes effectively a short circuit. So this signal here will pass through the diode. It's riding on the back of the voltage that's delivered from our power supply. So it passes through. And if you go up to the oscilloscope over here, you can see, look, there is the sine wave on the oscilloscope, right? So what I'm going to do now is I'm going to take the voltage off. I'm going to take the bench power supply off. So it's going to remove that voltage from the diode. And look what happens to our signal. It's gone. The signal has disappeared. I'm going to reinstate the voltage, and the signal comes back. So as you can see, with this simple circuit, our diode can become a switch. All we have to do to turn it on is put voltage on here, and to turn it off, we remove voltage. When it's on, the signal passes through the diode because that 0.7 volts, what's called the barrier potential, that 0.7 volts is provided by the voltage, the current coming through here. And the signal rides on top of that, over the top of the barrier potential, and comes out there. Simple as. Again, this is a great use of capacitors because since we're feeding voltage in here, sometimes and not other times, we don't want that to influence our signal. So we put capacitors to block this current from going back into here or going out there. So by putting capacitors in here, we retain the fact that the signal is AC and not DC. Again, using capacitors, using diodes, the two components that we've looked at now. You might think, well, when would I use this? When is this ever going to be of any practical use in the hobby? And I'm going to draw a sort of an outline, a block diagram of when you could use a diode as a switch. And here's a really sketchy sketch. Okay, this is how we could use a diode as part of a FPV diversity. We use diode switches as part of an FPV diversity system. We've got a couple of video transmitters here, video receivers, sorry. Oh, what am I doing? That's an R, brain fade. A couple of video receivers here, antennas. They have an RSSI signal out, goes into a box here, which is our diversity controller, right? So that basically decides which one of these should be providing the signal. And out of here we have two voltages. We're not going to worry about the design of that at the moment, that's something different. But basically what this does is, if this is the good receiver, then this voltage will turn on. If this is the good receiver, that voltage will turn on. And we have our signal, our video signal coming down here through a capacitor. What a crap capacitor that is. Into the diode. The other one has the same thing. Its video signal comes down through a capacitor into this diode, right? So let's assume we have a nice strong signal on this video transmitter. The RSSI goes up. This little piece of circuitry here says, whoa, we want to use that signal. So it puts a positive voltage on here, which means that the current flows through there, through our diode, and then through that there down to ground. So we have current flowing through the diode. So the signal, as we saw, when we have current flowing through the diode, it also passes the AC, which is the video signal. So the video signal will go down here and out to our goggles through the connector. Right, say it all changes. Let's say this gets the strongest signal, right? So the RSSI and this goes up, RSSI and that goes down. This little box says, well, we want to use this signal. So it raises the voltage on here, a little resistor in series. So now we have current flowing through this diode, down there to earth. The current stops flowing through here because this voltage will drop because the diversity controller said, no, we want this. So then the video signal riding along here goes through a capacitor because it's AC, goes through that diode and out there. So these diodes effectively enable us to switch between one receiver and the other based on which one we put some current through. Brilliant, super simple. And you might say, well, I haven't seen diodes in diversity controllers, why don't we use them? Well, it's because there are better things to use now. But back in the day, and even today, in some circuits, especially specialist circuits, diodes are still used to switch small signals like video, like audio, like other radio frequency signals. They can be a very, very effective way of switching it. And they're so simple and cheap and easy. You can buy a bag of diodes, for a few cents. That's so super simple and cheap devices. And this is one of the seldom realized uses of diodes as a switch, as an electronic switch. Of course, because it's electronic, these switch incredibly quickly. And not like relays and so forth. But the downside is with a diode switch, you can't use it to switch DC, you can only use it to switch AC. So you've got this capacitor here and this capacitor here. So that even if the signal has some DC on it, then this capacitor will take that out because that DC would affect. If you had a voltage on here with the video signal on it, then it would automatically just turn this diode on, and that would cause the thing to basically it would defeat the purpose of the switch. So that's it, simple. Diode switch. Probably never thought you could use a diode as a switch, but it's one of my favorite uses of diodes because it's so unintuitive. You just don't think about it, really. It's something you just do not think about. Right, now I'm going to show you how to use a multimeter with diodes, because it's a great way to test diodes and also to determine what type of diode they are. So I've got a couple of diodes here. One's a rectifier and one's a Schottky diode. I don't know which is which. I can't read the tiny writing without my glasses. But if I want to find out, I go to my multimeter. And most multimeters have an ohms diode range. You can see it there. Go to that and you select the diode range, which means on this meter, puts a little diode up in the corner of the screen there now. It's in diode range. And what it does, it's not the same as ohms. It's not going to tell you how many ohms these diodes are. It's going to tell you how much voltage is being dropped across them. So if I put my meter across this diode, we've got 0.541 volts. So that's probably the rectifier. If I go across this one, whoops, let me get it right. Where are we? Oh, it's the wrong way around. It only conducts one way, remember, so you put it across the right way, and it says 0.181. So this obviously, with a much lower voltage, is the Schottky diode, and this is the rectifier diode. So now I know which one's which, and if there wasn't marking on here, I could even work out which way around they go, because they conduct from positive to negative. So with my positive lead on here and my negative lead on there, I know that the triangle points that way. And if you reverse your meter probes, generally speaking, you get nothing. You get nothing because the diodes only conduct in one direction, remember? On the Schottky, you still get nothing because they do have a higher leakage current. I'm just wondering if I put this back to ohms, maybe we can actually measure the leakage current, because there is a small amount of current that still flows. It's not a perfect conductor, not a perfect switch. So let's have a look. No, it's good enough that we're not able to measure how much current can sneak by when the diode is connected around the wrong way. And the same on this one, I suspect. Yep. So they're almost perfect, almost perfect. And that's how you can tell a Schottky from a power diode. The Schottky will have the lower voltage drop when you're in the diode testing mode. And if you get a diode and you test it and it measures the same both ways, it's buggered. Simple way to test. And here is a really practical example of what I was talking about, using a diode as a protection to stop you plugging things in the wrong way around. Now, in my Hobby King Tomahawk, love this little plane, I have an FPV system, which is up here, but one of the problems with some of these ARFs and these, especially the bind and flies, is that's the battery connection. There's no extra connection on there to provide power for your FPV gear, right? So you've either got to unsolder that and solder another pigtail on, or you can do what I do sometimes, which is I just make up one of these, this little lead here. So my FPV gear has a JST connector on it for power, right? It's a simple regular JST. And what I do is, to get the power on the other end here, to make a JST, I have this plug here, which, let me move this out of the way, is simply something that I can plug into my balance lead, see, on any battery. So by doing that, I can just plug this in here, and away you go. But if you notice something here, how easy this is to plug in backwards. I've just plugged it in backwards because I didn't have a proper balance lead connector, so I just used a bit of pin header, which is not polarized, so you can plug it in backwards. And as you can see from this, if you're in a hurry, oh my God, look, you've just put the negative to the positive on the balance lead and the positive to the negative. And if I plug that into my FPV gear now, you'd think, oh, it'll blow up, because it's all reverse connected. It will, let me pull that a bit. It will put the wrong voltage, reverse voltage into the FPV gear, and the smoke will come out. But it won't on this one. It won't, for a very good reason, because in this heat shrink here is hidden a Schottky diode in series with the flow. So if I plug it in the wrong way around, the diode that's inside there, you can probably see it within the heat shrink, that will block the flow of electricity. Electricity will not flow the wrong way through my FPV gear. Yet when I turn this around and put it in the right way, then the diode will be, the electricity will flow the right direction through the diode and everything will work just fine. I will lose 0.3 of a volt because that diode's in there, but that's nothing, because this is a, it's a 4-cell pack, it's got 16 volts. Losing 0.3 of a volt's nothing. And it means that there's no way I can accidentally blow up my FPV gear if I'm in a real big hurry and I just plug that in wrong. So that's what I do quite often. If I'm making up these little fly leads that go from balance leads to JSTs to power equipment, it might be FPV, it could be anything. Put a diode in there, put a Schottky diode in the positive lead and make sure you got it the right way around, so that even if you plug it in backwards, nothing's going to blow up. Now, as usual, I want to show you some diodes in action, but it's really hard to find diodes on modern electronic equipment. And there's a good reason for that. This flight controller, do you see any diodes? On a quick look, I couldn't find any, certainly not on this side of the board, because mostly the diodes are actually part of these large integrated circuits that we see there. The ARM microcontroller and the IMU unit. These have diodes in them, but they're part of the whole substrate. Just like you don't see separate transistors very often on circuitry these days, you don't see separate diodes. The only exception to that is probably going to be on the back here, where we have a power supply. And I think there's a diode there. I can't really see through the camera, but there'll be a diode or two in here. Because what happens here, this is a inverter power supply. So it's chopping stuff up into pulses, which effectively makes them AC, and then it rectifies and it uses diodes to have one-way flow of current. So you need to have an external diode to do that because they have to pass quite a bit of current when they're doing it. So there are some diodes down there, surface mount diodes, and surface mount diodes look like this. They don't have any wires poking out of them. They're designed to solder directly onto the surface of the board. As you can see, if I can tip this over, if it will cooperate without pinging off the board and disappearing forever. Come on. Yeah, they sit on the board and then the solder on each end there. So that's a surface mount diode. Again, they have a little white bar on one end so you know which way around they go. And look at that. Yeah. So yeah, there'll be one or two in this power supply here. And the same goes with any kind of circuitry that has a inverter power supply. So that's it. That's all you need to know about diodes if you fly RC models. Well, probably not all you need to know, but it's probably enough for today anyway. Really, really valuable, indispensable component, but it's one of the simpler ones. As I say, it's like we've done capacitors, now we've done these diodes, and next time I'll probably talk about transistors, which are even more clever and even more heavily used in modern electronics, because inside each of these ICs are literally, in some cases, millions of transistors. Individual transistors, of course, look a lot different. Here is an individual transistor, 3 legs. These were very common way back, but now, you just don't see that many discrete transistors in circuits. But that's something for another Tech Tuesday. Right. Thank you for watching. If you made it all the way through, I hope you've learned something. If there's any questions you've got, anything you want to know, then please put your questions and comments in the place provided by YouTube. I will do my very best to get around and answer them. I try to read them all and answer the ones that require an answer. In the meantime, if you've got ideas for Tech Tuesday, if there's stuff you'd like to know about, techie stuff, electronics, whatever, let me know. And I will be expanding this. I'm going to do maybe a mechanical Monday or something where I look at some of the other things that are really useful to the hobby in the way of tools and techniques and things. I mean, I have a workshop full of lathes, mills, the whole TIG welders, all that sort of stuff. I'm going to go through those and show you how you can use those in the hobby, the benefits of them, the downsides, which cost and so forth. And so maybe we'll give you a better indication of the tools you should have when you're building RC models. In the meantime, thanks for watching. Bye for now.